Hey there guys, it's True Redstone here, and after years of wondering, why can't I, just an average redstoner, sort of, I guess, build a computer in Minecraft? Well, I've finally answered that question. As you guys may have noticed, I have kept this project a secret for quite a while recently, only giving quick hints in my multiplier video, where I showcased the 16-bit CCA. And, well, if we go down here and look at this, what we can see is exactly what we saw in the 16-bit CCA video. So, now, let me show you guys the full project in all of its beauty. So, obviously, I'm not starting with a showcase. I will do a showcase at the end, but at the current moment, I will just be showing you guys the computer and how it works. So, here are just some of the stuff. These will be shown in the showcase, but whatever. This is a call stack. It allows for recursion up to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Allows for recursion up to 16 deep, stores 10-bit numbers. And this is the program counter. It is 10 bits. And it is able to call, and it is able to jump directly from here. Let's see. It also has It also has a setting, basically, which just tells the program what to do on each instruction, which are the top 4 bits. I will link the instruction set down in the description for those who want to try it. And we have all of these. And then we have our program counter display. It only goes up to 15 though, because I didn't want to get too much into signal strength here. Then we have our instruction memory, sorry. It supports up to 1024 lines of code, or not lines of code, instructions, basically. So this allows you to run pretty large programs, such as like Tetris and stuff, and that is because of this 10-bit decoder and everything. It has a 200-tick clock with start, stop, step, and reset for all of them. And once it hits a halt, it will also reset the CPU. So it has multiple instructions too, which we can quickly go through. No op, nothing, halt, stops the computer, add, adds 2 numbers, subtract, subtracts 2 numbers, NOR, and XOR, right shift, load immediate, add immediate, jump, branch, call, return, load, and store. And this is 15 general purpose registers. Register 0 is 0 register. Dual read. Both go into the AOU. 8-bit AOU with 2 flags, carry, and 0. And then settings, different settings, invert B, invert A, or carry in, flood, carry, right shift. Then we have our output, which then goes back into our register file, which also has an input for loading the RAM into here, or data memory, and just loading immediate. And for add immediate, we would read one of these, and we would allow this in from here, which would add the 2 numbers together. And then this basically just goes into the RAM right here, and just can load the RAM. And then we can also have offsets using the AOU, which will compute register for the pointer. The register is the pointer, and then you can have a 4-bit offset, which will then be computed and then thrown into here, which is then where it will be written, enable, clock, whatnot. And then obviously 256 bytes of RAM, basically. You could call it RAM, or you could technically also call it data memory. They can be called multiple things. For the output, we have registers 240 to 252 as our outputs to what will be the screen soon. I haven't built the screen yet, though, because obviously I want you guys to kind of learn something from it too if you guys download it. So I will make a video on how to make binary screens, but I want you guys to make screens for the computer that you guys can use if you download the computer. And then that's basically it for the most part. So I think we probably want to move on to the showcase. So I'll see you guys in that showcase.